Continue. Admit. Okay. Got everything arranged. Okay. We will go ahead and get started here. So yes, handouts up front, up here, for those of you who like handouts. The handout comes from the topic 5 folder in the notes validation.pdf. That is the handout. And today so last time we were going over the nearest neighbor. We've been going over all of these model zoo notes here, multi-layer perceptron, all the tree stuff, and then last time the nearest neighbor. We'll finish up the nearest neighbor stuff today, and then maybe finish, maybe not finish, but at least start the validation notes over here. And this will be the last new material for the semester right here. Most of next week will be final exam preparation about stuff. If you haven't signed up for the final exam time slots, please do that. Anybody have questions about anything administrative? What to expect last 2-ish weeks of the semester?
Assignments still due December 1st.
Assignments still due, yeah, the end of break, Sunday, the end of break. Everybody's ready to have a big, long Thanksgiving break here. Sick of, obviously not sick of data mining, but sick of all of your other boring classes. Okay, well, let's see. So this is I want to look at that. So again, our model zoo notes here, we started off looking at a picture, looked something like this, and this picture, what it's showing us is all the different decision boundaries of these different models. And we were looking last time at the nearest neighbor decision boundary over here. One of the nice things about nearest neighbor is that it's both really simple to describe and use, and the decision boundaries can take on any sort of shape that might be convenient for us. Coming over here is the model 3 notes they were looking at with this nearest neighbor. And one of the things that we talked about was there's the idea of one nearest neighbor versus k nearest neighbor. The one nearest neighbor only looks at the most close data point to determine the classification of new data points. The k nearest neighbor looks at the k closest data points and takes the average of those, or has some sort of rule to aggregate those together. That rule could potentially weight closer data points more than farther away data points. But the theory, the intuition, it doesn't really depend on how those data points are aggregated. It's just how many data points are there that's important. And one of the things that we talked about is if you have one nearest neighbor, you're very sensitive to noise, in that if you have some sort of outlier data point, like this pink magenta plus that I drew right here, all of these points over here, they sort of should be gray, is what we were talking about before. This area should be gray. Should be negative, but if you have an outlier data point, this one nearest neighbor is going to make all of this stuff over here be labeled as positive instead of as negative. So one nearest neighbor, more sensitive to noise, and as you make k increase, that noise becomes less of a problem. So that's one of the main takeaways of k nearest neighbor, how to handle this k, what this k is doing. K increase implies noise is less of a problem. Another difference between k nearest neighbor and some of the things that we've talked about before is the algorithms that are used for doing k nearest neighbor. There's these basically 2 categories of algorithms you can use. The brute force, which means you're always calculating the distance between every data point in your data set every time you're doing a labeling. So that's theta of d in runtime to do label one data point. Or there are various data structures for trying to make this fast, the goal trying to get logarithmic and in. The scikit-learn implements ball tree and KD tree. Neither of these have like guarantees associated with them, and so we can't actually guarantee login, but it's almost login in practice. Downside of this is that we have this curse of dimensionality here of 2 to the d. Whatever your dimensionality is, if you're using one of these clever data structures, your runtime is going to be exponential in that dimensionality. And so that's the first curse of dimensionality here with our nearest neighbor methods. Then we started talking about some of the statistical facts of nearest neighbor. One of those is that the VC dimension is infinite. And so because the VC dimension is infinite, our standard generalization bound is not useful for one nearest neighbor. And it's also true for any value of k that the VC dimension is going to be infinite. And so this generalization bound, like we had been talking about, is not useful. But there is still things that we can say and prove about nearest neighbor. That's this theorem 1 talking about that. The important thing here about this theorem 1 is that it's not comparing our out of sample error to the in sample error. Instead, it's comparing the out of sample error to the Bayes error. Both equation 1 and 2 right here comparing the out of sample error to the Bayes error. And in blue right here, the summary is that if you're doing one nearest neighbor, you can't do better than twice the Bayes error. So one nearest neighbor potentially good for problems with low Bayes error with very little noise, but as you add more noise to the problem, one nearest neighbor is definitely not going to be the tool that you want to use. So that's what this blue portion of the equation was talking about. The red portion of this equation was talking about another curse of dimensionality that it's a little bit hidden here. We'll zoom in a little bit more. This d right here in the exponent for the n over here, it's not like in the previous bounds we've seen, it's 1 over the square root of n, but this is 1 over the dth root of n. And so this results in exponential dependence in d. As the number of dimensions increases for nearest neighbor, then the number of data points that we need also increases exponentially. And so for nearest neighbor methods, there are 2 curses of dimensionality, this computational curse of dimensionality. That can be important, but really it's the statistical curse of dimensionality that is the more important one. Because computation, you can resolve that by just running things for longer. But statistical curses of dimensionality, if you have a bad generalization bound right here, there's no way to resolve that except for more data, and more data is usually more expensive than more computation. So again, the nearest neighbor, different style of generalization bound compared to the standard VC dimension generalization bounds we've talked about for most of this course. And there are some problems here about using the nearest neighbor method. One of the things that we mentioned, but we didn't work through any of these problems, is that if you are using nearest neighbor, very common to combine those with dimensionality reduction techniques to counteract this curse of dimensionality. And again, that'll counteract both the statistical and the computational part of the curse of dimensionality. So very common if you're using nearest neighbor to combine with dimensionality reduction. And then we started talking about the support vector machines, and we'll finish talking about those today. 3 equivalent ways of talking about support vector machines. This method 1 over here is we talked about this maybe about a month ago in class now, where a hypothesis class, or what a support vector machine is it's the hypothesis class H-perceptron, where you are learning that hypothesis from the hypothesis class using the hinge loss, which is defined right here. We talked about this when we were talking about gradient descent versus stochastic gradient descent versus second gradient descent, 2GD. We also talked about this in comparison to logistic regression, that both the hinge loss and logistic loss for logistic regression look very similar to each other. So the support vector machine and logistic regression will typically have very, very similar in-sample errors. And both of these losses are convex and surrogate losses of the 0-1 loss. The advantage of the hinge loss is it is the most robust possible loss. The advantage of the logistic loss is because it has this extra curvature right here. The reason that curvature exists is it gives it this probabilistic interpretation. So logistic regression has a probabilistic interpretation, which we didn't explicitly cover in class, but I mentioned the book has a decent discussion of that. The SVM with the hinge loss has no probabilistic interpretation. But SVMs, this part 1 of the SVM, is very, very similar to logistic regression. And so today we'll continue talking about these part 2 and 3 equivalent definitions over here. 2, we talked a little bit, started talking about that last time, this idea of the large margin classifier. And this picture that we drew last time, we have these data points, all these pluses in the top right and these negatives over here. There's a linearly separable data set. And we talked about how the perceptron learning algorithm, the PLA, is not guaranteed to, in any sense, find us the best of the hypotheses with zero error. It's just going to find us some hypothesis with zero error. And so any of these magenta lines right here, those are valid hypotheses for the PLA to return. But the support vector machine, one of the nice things about it, the reason it is a large margin classifier, is because if the data is linear separable, it's guaranteed to give us the hyperplane that separates the data with the largest margin. And again, this rho value, this like squiggly looking P right here, is a rho, Greek letter rho. And the Greek letter rho is standard for the margin, the distance between the hyperplane itself and the closest data point. So the support vector machine is in some sense a generalization also of the perceptron learning algorithm to get us the best of the data points, or the best of the hyperplanes that is maximally far from those data points. And then we finished up last time, I mentioned this theorem 2 right here, which gives us a generalization bound for the support vector machine. This generalization bound is closely related to the ones we've seen before because it's in particular giving us a VC dimension right here. So this VC dimension immediately implies the bound on the out of sample error minus the in sample error. This formula right here implies the bound on our generalization with the standard VC generalization bound. What's nice about this bound though is that this bound, so this R squared over here and rho, it's based on these properties of the data right here. And the property that is not present is the dimension. So we have a bound on our VC dimension that is independent of the dimensionality of our problem. Again, the R squared is the radius of the data set. So coming up here, this R is the radius of the data set and centered at the origin, not centered at the center of the data. But this ratio, R squared over rho squared, somehow determines the generalization capability of the support vector machine. I also mentioned last time that so the textbook has these E chapters, they call them. The printed textbook has 5 chapters in it, and then there's another 6-ish chapters that are only in PDF format. And all of the things that we've covered so far in this Model Zoo come from those 6 extra chapters. Most of the material in those 6 extra chapters, very dense, not worth reading. But one of the parts that is worth reading is their description of Theorem 2. I think it's very intuitive, and so it's worth taking a look at that to properly understand why Theorem 2 is the way it is here, and being able to take advantage of it. Okay, and that's where we left off last time. We're gonna talk next about this part 3 of the support vector machine and how it is a smooth generalization of the K nearest neighbor algorithm. Amika.
Sorry, I was just thinking about this.
Mm-hmm.
We're always like VC as like discrete value, like for n, like sense or whatever. But R and rho could be like 1 values.
Oh yeah, so there's a good question here, and I'm going to answer it in 2 parts. The question is with this, like basically this R squared and rho squared, they're somehow dependent on the data. How's that interact with this VC dimension here? And the first part of this question is R and rho don't necessarily have to be integers, like nice numbers. And these little half square bracket things right here, this symbol in the equation, this is supposed to mean the ceiling function. And so something like 1.1 would be equal to 2. And so the VC dimension here is still going to give us an integer number, and so it still fits with our definitions of VC dimension that we've talked about before that assume that the VC dimension has to be an integer. So that's one weirdness about this equation here. Another weirdness, though, is that this like r squared and rho squared, these are somehow dependent on the data. Like the r squared and rho squared of this particular data set right here is going to be different than the radius and the margin of a different data set. And the way we've talked about VC dimension is that it should not be dependent on the data in any way. And so one of the things that the textbook talks about in this section about what's in their chapter 8, theorem 8.5, is what they do to make sense of this, of making these quantities here actually not dependent on the data, but some more abstract-ish thing. Yeah, so if you feel uncomfortable with the fact that the VC dimension here is dependent on the data when our other definitions were supposed to be independent of the data, then this reading their discussion about theorem 8.5 in the textbook will hopefully clarify that or make you more comfortable with the fact that this is a data-dependent bound. It ends up being just like a notation trick that they redefined the hypothesis class in a way that makes it equivalent to only working on data with that satisfies this r squared or rho property. But good question. Did that answer your question? Any other questions about anything? Yes, Jeff.
The relationship between why the SVM is the best classifier and DBC. So SVM is the classifier that maximizes row, right? And going down to the equation again, a larger row would mean a smaller upper bound on the DBC, but don't we want our DBC to be bigger generally so we can shadow more data?
Yeah, so there's a great question. The question's two parts. The first part here is connecting this equation back up to the picture. And anytime we have pictures and equations, connecting them back to each other is like the first thing you should be doing in your head, thinking about these. And so excellent, perfect thought process here. And so then the second part of the equation is like, why do we want rho here to be in the denominator and not in the numerator? Because if rho is in the denominator, then the farther away we are from the data, then the smaller the VC dimension becomes. And the answer is that we don't always want our VC dimension to be larger or always want our VC dimension to be smaller. There's always and so part of the question was like, if rho is large, and that correctly implies that the VC dimension goes down, doesn't that mean that we shatter less data? Or we shatter fewer data sets? And the definite answer to that is a yes. So all the logic there is perfect so far. But then the question is like, why might we want that to happen? And so why might that be good? Why is that good? And the answer is that this might cause our in-sample error, cause the in-sample error to be high. But it will also cause the generalization error to be low. E in minus E out, the generalization error to be low. And so depending on our particular problem, we might need the generalization error to be low. If we're already in the overfitting regime, then that means that our in-sample error is already low, and the out-of-sample, the generalization error is too high. And usually that's the more important case. So when we're putting this upper bound on the VC dimension, we're putting the upper bound on how bad can our generalization error be. And again, usually like the in-sample error, that is something that we know, easy to calculate. And so if we know our in-sample error is say 0 and our VC dimension is very, very small because our margin is very, very large, then we're very confident that we have a very good classifier that's going to do well in the future. So all the reasoning that you suggested was correct. It's just that we very often, more often than not, are more concerned about making the generalization error small, especially in these like mathematical proofs about things. Okay, great questions. So then what we're going to do next is connect this, our discussion of support vector machines back to our discussion about nearest neighbors. And so, and two of these, there's 3 packets here of the model zoo notes, and I've tried to group the models together in some sort of logical order. And so the things that are connecting the support vector machine to the nearest neighbors, 2 connections that we'll see. The first connection is they have weird generalization bounds. So the nearest neighbor generalization bound based off of the Bayes error, and the support vector machine generalization bound based on the radius and the margin here. So that's one thing that's, I guess, connecting these 2 models to each other. The next thing that's going to connect these 2 models to each other is this part 3, and how support vector machines are this smooth generalization of the K nearest neighbor algorithm. And we will talk about that at a very high level in this problem 4 right here about the dual learning problem and the kernel trick. So first, we're going to talk about this dual learning problem. What does this mean? Let's remind ourselves about our hypothesis class of half planes. Our linear hypothesis class, or our perceptron hypothesis class, has a lot of different names. I'm just going to rewrite that hypothesis class right here, which we have seen many times at this point. So X into W transpose phi of X. So this version is including the feature map already built inside of the hypothesis class right here. And our W is contained in R. In this case, it's to the D tilde, like this. The D tilde, again, being the dimension of our phi map, this phi function taking R to the D into R to the D tilde. So this is just our standard notation. Everything that I've written so far, standard notation for us, and I'm just reminding us of what that notation is. And the dual learning problem is the observation that there is something called a, well, there is a theorem that is called the representation theorem, and I will write that out, and then we will see how that representer theorem allows us to modify this problem up here. So the representer theorem goes by many, many names that are effectively synonyms with this. So the representation theorem, representer theorem. Sometimes there's a name associated with it. The main person's name is Mercer. The Mercer representation theorem. Sometimes it's associated with various spaces in mathematics, like Hilbert representation theorems or Banach space representation theorems. But if you see anything in the textbook or anywhere else that uses something like the word representer, it's always this theorem right here. And that is that the optimal W star, so again, the star or asterisk on a variable, meaning that it's the optimal, so the one that minimizes, in this case, our in-sample error, is you can represent this as the sum. So from I equals 1 to n, alpha sub I, v of x sub I. Here, these alpha, each of these individual alpha sub I variables, these are real numbers. Alpha sub I is a real number, and so that implies that the alpha variable without a subscript is a vector. The alpha without a subscript is a vector in R to the D tilde. And again, this phi function right here is our feature map that is taking all of our data points, projecting it into some larger data space. But the output of this phi function is always in the r to the d tilde, and that is the same dimension as w, w contained in r to the d tilde. And so no matter what the w value is, instead of representing w just as a vector in r to the d tilde, we could represent w as this alpha vector, which is like some coefficient that we multiply all of our data points together. So each data point, another interpretation of this is each data point has some particular weight right here, and you sum all of those together, and that gets you your optimal W star. If you do this and substitute into the hypothesis class, then the hypothesis class will become h of x into this. So I'm substituting right here all of this red part in for the w. So the sum from I equals 1 to n alpha sub I phi of x sub I, like that. All of that transposed times the phi of x. This second x is the x that is being input into our function over here. These x's right here are the x's in our data set. And now the parameter that is the thing that controls our problem is these alpha sub i's. So alpha now contained in r to the n, the total number of data points in our data set, rather than d tilde, the dimensions of our problem. And this is the dual representation, or the dual version of our hypothesis class, or the dual problem. In machine learning, data mining, anytime you see somebody talk about the dual problem, it means they have done this substitution into their hypothesis class. And instead of learning an individual vector directly, instead of learning W directly, they are learning these alphas, these individual weights on these for each data point. Up we go.
I'm confused about what learning alpha is doing because I thought W is the weights, and then the alpha also is weights.
Yeah, so the question here is, what's the difference between learning alpha versus learning W? And the answer is that there is no difference because either in the primal, so this version up here is sometimes called the primal and dual are opposites of each other. This is called the primal problem. In the primal problem, we are directly learning the weights, which are the importance of like each feature. This W right here is again a representation of how important each of the features in the output of phi is to our classification accuracy. And so in the primal problem, it's like we're learning the importance of each feature. But in the dual problem, instead of learning the importance of each feature directly, we are going to check out how important is each one of those data points in our data set. Each one of those data points has a bunch of features associated with it. And so if we do learn this alpha vector, then we could recover this W star vector by this formula right here. And if we have the optimal alphas, plug them into this formula, then we will get the optimal W star. So these alphas, the alpha values and the W value are somehow representing the same exact information. Another way of thinking about it is that this function right here that I have in magenta, this function right here will always evaluate to the exact same result as this function right here, assuming that W is defined this way. So whether you're learning the W or learning the alpha value down here, whether you're learning the importance of each weight of each feature, or whether you're learning the importance of each data point in order to determine the function, either of those get you the same function at the end. Yeah, a lot of math fancy-ish math goes into proving that this result right here, that every W star can in fact be represented this way. But once, if you accept this fact right here, that every W star can be represented this way, then the fact that every function can be represented this way in terms of alpha instead of just this way in terms of W should be straightforward. Jay?
For the dual problem, what makes a data point more important than any other?
Yeah, so that's a good question about, for the dual problem, what makes a data point more important than any other? And the answer is, at a literal sense, if alpha I, in this case, the magnitude of alpha I greater than the magnitude alpha j, that's equivalent to saying that the data point I, data point x sub I, more important than x sub j. And so that's, in some sense, just kind of like punting your question, that it's, it begs the question about like, why might some data points have larger alpha values here than others? And it turns out that, and one of the things the textbook goes into an obnoxious level of detail on, which we will not. I'll scroll back down here in a little bit so you all can see that again. But I'm coming back up to this picture right here. The reason support vector machines have the name that they do is because if there are certain data points that are close to the margin, so let's say there's, so again, the red pluses and minuses form my data set. If there are, say, 2 more minuses right here and 2 more pluses right here, these 4 data points right here, I'll circle them in black. These 4 data points right here are somehow the most important data points because they are closest to our separating hyperplane. And these data points are also called the support vectors of the support vectors of the hyperplane. Any data point whose distance to the hyperplane is equal to the margin is a support vector. So the meaning of being a support vector here is that the distance from x to the hyperplane, to the decision boundary, I'll just write HP for hyperplane. Distance from x to the hyperplane equals rho. That is the definition of a support vector, what it means to be a support vector. And so actually now answering the question, which is what makes some data points more important than other data points, is that these support vectors are the most important data points, and those are going to be the ones, the data points with non-zero coefficients, alphas. All of these other data points that are really far away, they have no impact on what maximizes the margin here. And so the alpha values for all these data points can be set to 0. They won't have any impact on where this hyperplane is actually located. So the support vectors right here, the vectors, the data points that are closest to the hyperplane, the data points whose distance to the hyperplane is the margin, those are the most important ones. And scrolling back down here again, so for the alphas, the details depend exactly on how the optimization is done. But in general, for the alpha sub I, if that is not equal to 0, or if that is equal to 0, that implies that the data point x sub I, not a support vector, and so not important. And then the converse also true, that if alpha sub I not equal to 0, then that'll be equivalent to saying somehow that vector is actually important. It's going to contribute to where the hyperplane gets located, and so that is a support vector. Does that answer your question?
Yeah. For the second one, alpha sub I is not equal to 0 or alpha sub I?
Okay, so yeah, here I wrote alpha sub I not being equal to 0. That is, the alphas will not be equal to rho. The alphas here are not the margin values. It's not the distance to the hyperplane. The alphas are something else that doesn't have an easy interpretation. So you can't be more specific than what I wrote here. Okay.
Alphas not scalars?
Question is, are alphas not scalars? And they are in fact scalars. Each alpha sub I is a scalar. The alpha without the subscript, that is the vector whose length is the total number of data points. And so the distance here from this point to the hyperplane, that is the quantity that is important here. So the distance being a scalar. And so the distance could possibly be equal to rho over here. The data point itself is what we call the support vector. So alpha is not the support vector, it is the data point itself right there that is the support vector. Good questions. One last, I don't know, confusing twist here is that everything that I've just said assumes that there is actually a separating hyperplane. In general, there is not going to be a separating hyperplane. If you have vast majority of interesting problems, like we talked about, the PLA will not converge on those problems because there is no separating hyperplane. And you will still have support vectors, and you will still have alpha values who are equal to 0 and some equal to not 0. The definitions get a little bit more complicated, and they're not worth us going into detail here. So the high-level takeaways are, again, this representer theorem says that any optimal parameter value can be decomposed as a sum of, and it's actually any parameter value doesn't necessarily even have to be optimal, but it's also true in particular for the optimal. But any parameter value can be decomposed like this as the sum of the data points. And so if you learn the weight of the data points instead of the vector itself, you're doing the dual problem instead of the primal problem. And many of those alpha values will be equal to 0. And so this vector here, this alpha value, will be a little bit simpler than just a, it will most likely have many non-zeros, most likely have many zeros inside of it. Alpha is most likely sparse. So that is the dual problem. We have one last definition right here, the kernel trick. And the kernel trick is the main reason people care about the dual problem. So let's talk about the kernel trick. The kernel trick is to observe here in this formula that we never do anything on the data points themselves. We never are doing direct computations comparing two individual data points. And instead, the only thing that we are doing is comparing the projection of those data points on this other space. And so if we had a function, here's what the kernel trick is. The kernel trick is to come up with a function k from x1, takes x1 and x2 as parameters and outputs a real number. And it is going to be defined as, so k, x1, x2 as phi of x1 transpose phi of x2 like this. If we had some k function that was equal to this right here, then we could rewrite our hypothesis class, again, in the dual form. So this is the dual version of the hypothesis class, as x into now the sum from I equals 1 to n of these alpha sub i's of k, x1, comma, sorry, this should be a x sub I right here, x sub I, comma, x, where alphas in are to the big N. Again, the x sub i's, these come from the training data. And this x right here without a subscript is the input to our function. So this x right here is the same as this x right here. These x's come from our training data. And the kernel trick is useful both computationally and statistically. Computationally, it's useful because it's often the case that k here will be much faster to compute than phi. The case that k is faster to compute than phi. And in particular, for a lot of very interesting kernels, it's often the case that our phi has infinite dimensions. There are interesting kernels. So interesting k functions, I'll just write k here for kernel, where the corresponding phi is an infinite dimensional function. So it takes r to the d into r to the infinite. And this would be something that is impossible computationally to actually compute. We'd be running forever trying to compute this phi value. But if we have access to the kernel, there are many constant time kernels that have an infinite dimensional representation. Yeah, I'll scroll down here in a second to see some more examples of these kernels, and that will hopefully make some of this discussion more concrete. So this table right here, these are 4 standard kernels. These are the 4 kernels by default implemented in scikit-learn. And the linear kernel here is the simplest of those kernels. It's just a simple dot product right here. So this is equivalent to no feature, equivalent to no phi. The linear kernel right here. And so the feature dimensions is d tilde is still just equal to d. We've talked about the polynomial kernel in the past, and we specifically talked about it as the polynomial feature map instead of the polynomial kernel. It turns out, though, that this kernel right here, this k function right here, is equivalent to the polynomial feature map, and this is much faster to compute. The runtime, let's see, it'll come down here like this. The runtime for computing phi for the polynomial kernel is theta of d tilde, which is again the theta of d to the q. But the runtime up here for this function is linear in d. The runtime for that particular kernel, all we have to do is take a dot product. That gives us a scalar, scalar plus a scalar's constant time, raise a scalar to a power, also constant time. So the runtime for k here, the kernel, is just theta of d. Much, much faster than the d to the q right here. The feature dimensions, d tilde over here, again, the same as the feature dimensions for the polynomial kernel. And then there's these 2 new feature maps right here, the Gaussian and the sigmoid feature maps. There is no easy to define phi function for either of these 2 functions right here. You get a phi function by taking the Taylor series of these, which is obnoxious, and so we won't do it. But the important thing is that they are infinite dimensional feature spaces here. If you're using the Gaussian or the sigmoid kernel, then your data set is implicitly living in an infinite dimensional feature space. And computationally, that would be impossible to realize. But with this kernel trick in the dual space, this is very fast to realize. Either of these 2 kernel functions are linear time to to run. Essentially, all kernels that people use in practice, linear time to evaluate, linear in the number of dimensions. Ambika?
How do we apply a kernel to go down in dimension?
Question is, can the kernel reduce the dimension? And the answer is you could use a kernel to reduce the dimension, but nobody ever does. The kernel trick here is specifically for those feature transformations that increase the dimensionality.
What are x1 and x2?
Here, the question is, what are x1 and x2 in this k function? So k is defined generically for any two data points in your feature space, in your data sets. So x1 and x2 just generically any two data points. In practice, what the data points are going to be is that the first one is going to be, when you're in this dual form like this, the first entry in the first parameter here to the k function, to the kernel function, is one of your training data points. And the second entry over here, x, is the parameter that you're actually trying to classify, passing into the function. So the kernel function, just like the phi function, takes in data points from the data space. This is admittedly a lot of things to take in here. Very understandable if it is not 100% fully obvious about why exactly, or first of all, what all of this is doing, or the why to care about it. Again, the textbook does have a section here in chapter 8 about these support vector machines. They go into a lot more detail than all of this mathematically. They specifically go through all the proofs of the representer theorem over here and the primal versus dual representations in the kernel trick and why all of these things are equivalent to each other. A lot of complex math there, so that may or may not be helpful to you. The bigger picture overview reference for this is the scikit-learn documentation, which does describe still the dual learning problem here at this more higher level of generality. Yeah, so those are the two best references for this portion of the course. Let's see, so connecting this back to my original claim here about these support vector machines are a smooth generalization of the k nearest neighbor algorithm. Smooth generalization of the k nearest neighbor algorithm. One interpretation of this Gaussian kernel right here, one interpretation of this Gaussian kernel is that when you're doing the classification, so I'm going to redraw the moon, two moon data sets like this that we talked about for nearest neighbor classification, is that when I pick a new data point here that I want to classify, pick say this point right here, we want to classify this black point here as should it be positive or should it be negative. It's in sort of a weird zone right here where it's maybe not exactly obvious what we should pick. So it's that's why I picked this location right here. The way the support vector machine in this dual problem with the Gaussian kernel, the intuition about how it's going to do that is it's going to pick every one of our data points in our training set, and it's going to sort of put a Gaussian distribution on that data point. So this data point right here will have some sort of Gaussian distribution about how influential it is. This data point over here farther away, some other Gaussian distribution about how influential it is. This one way out here at the end, some Gaussian distribution, some Gaussian distribution. And these data points over here that are closer to our data point right here are going to have a much higher impact on our classification because this Gaussian is just a higher value right here for this data point than it is for this data point over here. So it's one way of thinking about it is it's like a nearest neighbor where there's a weighting based on these Gaussian distributions. Have we got-
When we originally learned about k-means, we did a question someone asked about like weights, and it seemed like the answer was it makes no difference to what it's to k-means.
So yeah, with k nearest neighbor, it's possible to assign weights, and there are different ways of assigning those weights. Inside of scikit-learn, the only way of assigning weights is either everything in the circle right here is equal or just linearly based on the distance. And I mentioned that either of those two options basically give you the same result. So two differences there between nearest neighbors and this Gaussian kernel support vector machine. One is that instead of doing a linear like interpretation of the distance, it's this very nonlinear Gaussian where things that are very far away are going to be extremely downweighted because the Gaussian grows very, very slowly. And things that are closer are going to be very much more highly weighted. That's one reason why the SVM is a little bit different than the nearest neighbor. The other reason why the SVM with the Gaussian kernel is a little bit different is because of these alpha values right here. So every data point will be weighted a little bit more differently. All of these data points would have high alpha values. A data point that's like a plus over here, this would have a low alpha sub I because it's like in a non-important region. All of these data points right here, low alpha sub I's because there's we just know it's going to be plus. There's not a lot of interesting things going on right here. And so this data point right here, we can just have a large alpha sub I, all of these be 0, and we don't really even have to consider these ones over here. Any data point that's on the sort of the edge of the decision boundary, I'm not calling it close to the margin because it's not a linear hyperplane in this two-dimensional representation, but any point that's close to the decision boundary will have a higher alpha sub I, and so it's both the alpha sub I and this like nonlinear shape here that are important and that make it a little bit different than the nearest neighbor. If we come back to our plots up here and look at how these plots of the support vector machine compare to the nearest neighbor. So this is the three leftmost pictures up here that we'll be looking at. The middle one over here, the linear SVM, you can see that the linear SVM again is basically equivalent to logistic regression, which I don't think even has an entry. It does not have an entry over here. Linear SVM finding somehow the best linear separator here for this data sets. And these top two data sets not at all linearly separable, so that the linear SVM can't do a good job on either this circle data here or this 2 half moon data set up here. Nearest neighbors does have strong decision boundaries over here that seem like they mostly follow what our intuition would expect. The RBF SVM, RBF is a synonym, so RBF stands for the radial basis function. It is a synonym for the Gaussian kernel. RBF and Gaussian kernel, the same thing. And you can see that this decision boundary for the RBF SVM looks very similar to the decision boundaries of the nearest neighbor, except that there's more weight being placed definitely on the inside of these regions. Places that are far away from the data don't have strong decisions associated with them. And there's, in the regions where there are strong decisions, more uncertainty as well about the classification. Nearest neighbors is basically always a hard yes or a hard no, hard red decision, hard blue decision. The radial basis function over here has a lot more flexibility or a lot more uncertainty sort of built into its representation. Go ahead.
Can you go over on a high level again, like how the alphas are found, or like whether we find the alphas first? And then, because it seems like to me, we find a plane and then base, or like find some boundary based on where the points are located. Those become the SVM that are, like I'm just, it just seems cyclical. I'm not sure what's first.
Yeah, so the question is, how exactly does finding these alphas work in practice? And the simple but unhelpful probably answer is that it's just stochastic gradient descent. SVMs are always done these days with stochastic gradient descent. And stochastic gradient descent can optimize any representation of any function. It's just we're plugging in this version of the function right here into SGD instead of the primal version up here. And so you can get the alpha values that way. But yeah, that's not probably super helpful because that doesn't help build a lot of intuition about what's going on. So one way of, well, let's see. So I'll highlight some like bad intuitions to make sure that you don't have, which might be helpful. So in this data set right here, we are in fact linearly separable. And so in a data set like this, you would never want to use something like any of these kernel functions right here, except the linear kernel. If you're already linear separable, then your E in is already going to be 0. You would never want something that has a larger representational capacity like one of these other kernels. And it is also not the case that these support vectors, they are not determined in advance in any way. The support vector, after we have already optimized these alphas, after we've already learned a particular hypothesis in the hypothesis class, then we could say that certain vectors are support vectors because they have non-zero alpha values. It will also be the case that for real data sets like these data sets over here, when you project these data sets into the very large or infinite dimensional spaces, every data point becomes a support vector. Every data point becomes equally distant to the separating hyperplane in an infinite dimensional space. And so it is, no longer useful to maybe try to think about where are the support vectors.
So we find the alphas using stochastic gradient descent, and then afterwards, and then when does a kernel come in?
So yeah, we find the alphas using stochastic gradient descent. The question is, when does the kernel come into that computation? Is that at every time we evaluate one of these functions right here to see what the current loss is, to see whether we should make the alpha be just a little bit bigger, be a little bit smaller, we'll have to call the kernel function on the data set that we're currently looking at.
So we're still adjusting the alpha.
If you change the kernel function, you would get different alphas, yes. Okay, let's see. So some big picture highlight takeaways about the SVMs here that you want to know are, and so this is related to what we're just talking about, the runtime and the memory usage properties. If you were to go through all the calculations about the runtime for using gradient descent for optimizing one of these loss functions, you'd get the runtime is theta of n cubed, and that'll be a capital N cubed, so it's cubic in the number of data points in your data set. So this is very, very bad for very, very large data sets. And so because of that, these SVMs with one of these kernel functions, nonlinear SVMs, rarely used on large data sets. There are approximate versions of support vector machines that make this runtime happen faster. But we're not going to cover any details about any of those. And the scikit-learn implementation obeys this theta of n³ property right here. When might you want to use support vector machines? So the place where SVMs remain state-of-the-art. Currently, SVMs are only state-of-the-art, SOTA, state-of-the-art, when the X values, the X data points, so X/ data points are not easily represented as a vector. Cannot be represented as R to the D for some D value. If your data can't be represented as a vector, then the neural networks, you can't use them because they assume that the input data is represented as a vector. Logistic regression, decision trees, all of these other boosting techniques, you can't use them because they all assume that our input data here, X, is represented as a vector. But our kernel function, okay, you can define a kernel function. Define K so that it just takes an X, there we go, X cross X into R, and you can plug that into an SVM and everything will work fine. So we're not going to talk in detail about any of these kernel functions. We're not going to talk at all about any of these kernel functions, but this is the only place that support vector machines remain state-of-the-art, and that's the main takeaway from this, is that you will see people talk about a lot of things about support vector machines. The math gets really complicated. We've only glossed at a very high level about all of the math, the most important takeaways of that math. The main important information about why SVM's not useful in practice on large data sets is because of the runtime here, cubic runtime. And so the sort of interesting tabular data sets that we'll be using on your final exam, you won't be using the support vector machine for, because SVM's not great in that region, in that environment. Yeah.
What is data that's not a vector?
Question is, what does data that's not a vector look like? Common example would be, let's see. So the way that the place that this is actually used very often is on DNA or any sort of genomic data. So if you have like two DNA strands and you want to know how similar are those two DNA strands, the state of the art for that is using support vector machines. There's not an obvious way to say convert a DNA strand from the AGCT representation to a vector representation. And so kernel function, easy way to compare two DNA strands to each other. A lot of graphs, like the mathematical version of graphs, there are good kernels for those. It's not easy to represent, say, a graph as a vector. It turns out there are a lot of situations where these non-vector data is the natural way of representing data, but yeah, it's complicated enough that we won't talk about them in detail. I don't know if that's helpful or not. Okay. That's everything about support vector machines, about nearest neighbor. I guess, yeah, let's see. Not a whole lot of time left. So we'll just do a quick pass through here. The bounds here, that's one of the interesting things about SVMs. the fact that the difference between the dual problem here and the kernel trick. Another interesting thing about SVMs and this runtime, last major interesting thing that you should know for the final exam. We're going to switch over now to talking about this chapter 4.3, validation and model selection. So we have just talked about a whole bunch of different models that can be used in these last 3 set of notes packets about the model zoo. And then this begs the question of how you decide which of those models to use in different situations. And so we're coming back to the textbook now, chapter 4.3, to talk about the best ways of selecting which one of those models to use. This PDF file, where it's located in the electronically again, is in topic 5 right here, this notes validation.pdf. And this is the last thing from the textbook that we will talk about this semester. So quick review about chapter 4. Chapter 4 again, sections 1.4.1 and 4.2 talked about regularization. And this was their key equation to motivate regularization, that this overfit penalty right here, this is what our regularization is attempting to estimate, this overfitting penalty, or the generalization error. Regularization estimates the generalization, the overfitting penalty, the generalization error. What we're going to talk about now, though, validation is directly estimating the E sub out right here. Directly estimating our out of sample error. And there's a lot of, a lot of new notation in this section, where the concepts are all super straightforward and simple, but the new notation can be a little bit overwhelming. So for the next couple of pages here, I have a lot of sections where it first talks about illustrate the validation set notation, or whatever the notation is for that particular section, and then a formula where that's the important formula about the notation, the key thing to understand. And we'll probably today have enough time to talk about this first set of notation, and that'll be where we'll stop. So one of the things that we've talked about so far is, or the standard setup that we've had so far, is that we've had a data set. D, script D is how the book has represented that data set. And this has been our training data. And then we had another data set that was our testing data. The book used D sub test, and that's our testing data set. The size of our training data set was the capital N with no subscript, and the size of our testing data set was the N sub test. The validation set is going to be a subset of our training data set. And so this first part of section 4.3.1 is introducing a bunch of new notation to describe this breaking up of our training data set into 2 parts. So I'll draw it down here, but this is like the same, this stuff in blue is just a breaking down of the stuff in red up above. Confusingly, the training data set is broken up into another part that is also called the training data set. The textbook uses D sub train for this, but the English word for this full test up here of size N and this set right here, they are both called the training data sets. And this second data set over here is called the validation data set. They use D sub val, or the English word for that is the validation set. The size of the validation set is of size capital K, and the size of this smaller training data set right here, D sub train, is N minus K. This is the size of these data sets. And previously, we talked about where the textbook used the letter G right here for this is a hypothesis. Hypothesis trained on all of D, the original training data sets. They're now going to introduce this new notation G minus for the hypothesis trained on just D sub train, which is this subset of the full training data set right here. Again, G has the size of D equals in data points on G, but then the size of D train being in minus K. And so their motivation for why they put a minus up here is because there are fewer data points. We have subtracted away some number of data points from our training set right here. The motivation for doing this, the motivation for splitting our training data set into two parts is that we will train or select our hyperparameters based on this validation set over here. And it turns out if we were to select our hyperparameters directly on the test set, then we would inadvertently overfit our data. And so this extra validation data set right here is going to help prevent us from accidentally, inadvertently overfitting our data. And the rest of this notes will talk about why that's the case with a handful of different equations, but we'll talk about that after Thanksgiving. And this is a good spot for us to stop here. So again, yeah, what we're going to be seeing in this last notes packet is breaking up this training data set into two smaller data sets and why we want to do that. If anybody has any questions about this, or probably more likely on the SVM stuff, I will stick around afterwards, get those answered. And otherwise, I hope you all have a good Thanksgiving break. And see you afterwards. Okay. I will still have office hours tomorrow at the normal times, and then I'll have extra office hours and review sessions available on next week, which we will talk about next week. But yes, office hours tomorrow at the normal time.